The scientific field has distinguished itself as one that is built on precise and repeatable processes, and this exactness has given us safety and comfort in many ways. But with the recent discoveries about supernovas made by the James Webb Space Telescope, many astrophysicists have been forced to scamper around for answers. These discoveries are essentially questioning the very foundation of physics as we have known it for hundreds of years. What are supernovas? What laws of physics is the James Webb Space Telescope attempting to break, and why should it matter to you? Join us in this video as we discuss how James Webb just found a supernova that could break the laws of physics. Supernovas are a rarity. You don't just wake up and find them like you would a cup of cappuccino or espresso at your favorite coffee shop. You would have to try a bit harder than that. As such, the concept isn't very popular at dinner conversations or a meet-up with friends, but they are essential because they give us hints into our universe and what goes on in it. But what are supernovas? A supernova is the explosion of a massive star at the end of the star's life cycle. When a massive star exhausts its nuclear fuel, it undergoes a catastrophic collapse, leading to either a supernova explosion or the formation of a black hole. These explosions are among the most powerful events in the universe, briefly outshining entire galaxies and releasing an immense amount of energy. Think of those movies you've watched of a gas pipeline or station exploding, and you're close to the right picture. But supernovas are on a much grander scale than a gas station explosion. So, of what importance is a supernova to our understanding of the universe? Well, apart from the formation of black holes and the release of massive energy, supernovas help to determine how fast the universe has been expanding since the Big Bang happened. Determining the universe's rate of expansion uses a phenomenon called gravitational lensing. Albert Einstein first predicted gravitational lensing in his theory of general relativity. It is an effect on light from a background source that arises due to the curvature of space-time. This curvature happens when the three dimensions of space and time are united into a single entity by mass. The effect is most observable when light from a bright background source, like a star, quasar, or an entire galaxy, passes by a massive object like another galaxy or a cluster of galaxies. This bending of light creates a gravitational lens, which can magnify, distort, or even create multiple images of the background object. Subsequently, several things can occur. It can make an object shift its apparent position in the sky over Earth or cause a single object to appear at multiple points in the sky. This would occasionally give rise to spectacular formations like rings and crosses made from the same object. More than this, gravitational lensing can also cause the light from a background object to be amplified. That means astronomers can use the gravitational lensing arising from galactic clusters as natural magnifying glasses. This magnification effect allows astronomers to study distant supernovas that would otherwise be too faint to detect and provides valuable insights into the expansion rate of the universe and the nature of dark energy. Gravitational lensing can also be used to study the distribution of dark matter in the universe. Since dark matter does not emit or absorb light, it cannot be directly observed. However, its presence can be detected from its gravitational effects on visible matter, such as the bending of light due to gravitational lensing. By analyzing the distortion of background galaxies caused by gravitational lensing, astronomers can map the distribution of dark matter in galaxy clusters and other cosmic structures. According to NASA, all these have made gravitational lensing a vital tool in investigating the universe when it was in its infancy. Light from the earliest galaxies that would usually be too faint to see has become observable by instruments like the James Webb Space Telescope and the Hubble Space Telescope. So here's what we know so far. First, supernovas are extremely bright explosions. Secondly, an extremely massive celestial object can distort or magnify the light that passes through it. Thirdly, this gravitational effect on light can help astronomers determine the location, distance, and age of certain celestial bodies. Now that we've established our background, let's go into how the James Webb Space Telescope's discovery of two supernovas is changing the fundamentals of physics. For decades, measurements of the universe's expansion have suggested a disparity known as the Hubble tension, which threatens to break cosmology as we know it. Nearly a century ago, the astronomer Edwin Hubble discovered the balloon-like inflation of the universe and the accelerating rush of all galaxies away from each other. Following that expansion backward in time led to our current best understanding of the Big Bang, which is how everything began. But over the past decade, an alarming hole has been growing in this picture. Depending on where astronomers look, the rate of the universe's expansion, a value called the Hubble constant, varies significantly. But with exact observations from the James Webb Space Telescope or the JWST, there is a new threat to the standard model of cosmology. The phrase standard model of cosmology is simply the most basic understanding of the universe. Think of something like the alphabet of space science, everyone agrees on it and builds up from there. According to Adam Rees, a professor of astronomy at Johns Hopkins University who led the team that made the new JWST measurements, it's a disagreement that has to make us wonder if we really do understand the composition of the universe and the physics of the universe. For reference, Saul Perlmutter and Brian P. Schmidt won the 2011 Nobel Prize in Physics for their 1998 discovery of dark energy, the mysterious force behind the universe's accelerating expansion. Let's go back a little. All cosmologists agree that the universe started with a bang. The young cosmos was formed in an instant, an expanding, roiling plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Technically, and left to their own devices, the matter and antimatter inside this plasma soup should have consumed each other entirely. However, scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity then compressed the plasma pockets, squeezing and heating the matter so that sound waves, traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded contents stretched spacetime, pulling a small fraction of this matter safely from the fray. According to the standard story that all cosmologists believe, as the universe inflated like a balloon, ordinary matter, which interacts with light, glued together around clumps of invisible dark matter to create the first galaxies connected by a vast cosmic web. At first, as the universe's contents spread out, its energy density and therefore its expansion rate decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an astonishingly fast rate. The cause, according to science, was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of spacetime. It is denoted by the Greek capital letter lambda. As our universe grew, its overall matter density dropped while the dark energy density remained the same, gradually making the latter the biggest contributor to its expansion. Together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda cold dark matter, LCDM, model of cosmology, which maps the growth of the universe and predicts its end. While many of the model's predictions have been proven to be accurate, there is one problem that seems not to go away. Despite much searching, astronomers have no clue what dark matter or dark energy is. According to Ofer Lohov, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is we don't understand the last two of them. But beyond this very basic issue, there is another more significant threat to the standard model of cosmology, the Hubble tension. It is discovered that the universe appears to be growing at different rates depending on what method astrophysicists use. In fact, methods that have been vetted and verified by countless observations have shown that the universe is expanding significantly faster than what the standard model of cosmology predicts. So the only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something, Rees said. To measure this growth rate, scientists use two methods. The first method looks at the cosmic microwave background, CMB, which is a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. According to popular findings, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump. But as the universe exploded outward, this soap bubble structure expanded into the cosmic web, which is a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant or dark energy. Plugging these into the LCDM model spat out a Hubble constant of roughly 6,200 miles per hour per million light-years. That is about 67 kilometers per second per megaparsec, with a megaparsec being about 3.26 million light-years. A second method to find the universe's expansion rate uses pulsating stars called Cepheid variables. These are dying stars with outer layers of helium gas that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan-Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. According to Wendy Friedman, an astrophysicist at the University of Chicago, it's one of the most accurate means that astronomers have today for measuring distances. To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then, astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 kilometers per second per megaparsec compared to the Planck measurement. Yet, Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. As such, some cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So when JWST launched in December 2021, it was poised to either resolve or cement the discrepancy. And with a mirror that is almost 3 times the size of Hubble's, it was well equipped to do so. Not only can JWST detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths. By comparing Cepheid variables measured by JWST in the galaxy NGC 4258 with bright type Ia supernovas in remote galaxies, Rees and his colleagues arrived at a nearly identical result, 73 km per second per megaparsec. Other measurements came back with respective results of 69.6 and 66.6 km per second per megaparsec. Friedman made one measurement with the Hubble Space Telescope on the rapid brightening of the most luminous tip of the branch red giant stars. Another was made with light bent by the gravity of massive galaxies. A separate result using the bending of light also gave a value of 73 km per second per megaparsec. The new result leaves the answer wide open, splitting cosmologists into factions chasing staggeringly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics in California only caused more frustration. According to David Gross, former director of the KITP and a Nobel laureate, we wouldn't call it a tensional problem but rather a crisis. Right now, there seems to be no way forward on this issue. Rees is pursuing a tweak to the LCDM model that assumes dark energy isn't constant but instead evolves across the life of the cosmos according to unknown physics. However, Rees's research, published in the journal